Hi, my name is Akash and I'm here to speak a little bit about donor spins and zinc oxide. The first thing we need to know is why do we choose spins to be the basis of our quantum information processing? Why should spins be the qubits? And the reason that we do this is threefold. Now, one is that the spins provide a long coherence time due to their weak interactions with electric field noise, phonons, and thermal radiations and similar stuff. They do also provide a great degree of quantum control due to their direct interaction with magnetic fields, both AC and DC, as well as with other spins. And in some special cases, they do show interaction with light. What the next part is, before I go into the further details about the technology, I want to do a thorough discussion of the existing competing technologies and what are their disadvantages as compared to zinc oxide. Now here are the list of existing technologies and their comparative disadvantages. Now the first we discuss NV centers in diamond. While NV centers in diamond have the biggest advantage of having the ability to operate at room temperature, they do have certain disadvantages. Mainly, the entanglement generation in NV centers is typically low and limited by non-ideal optical properties such as optical inhomogeneity, spectral diffusion, and low zero phonon radiative efficiency. Second, we come to donors in silicon. The donors in isotope purified silicon have promising features such as ultra-long coherence times and high fidelity qubit control. But the indirect bandgap of silicon makes photon-mediated entanglement and therefore the development of scalable quantum network challenging. While there are photon-emitting defects in silicon, the radiative efficiency is typically very low. And the next category is defect centers in 3-4 semiconductors. Studies of defect centers in direct bandgap 3 to 4 materials such as quantum dots and donors has demonstrated efficient optical transition, spin control, and spin readout. But because of the lack of spin-free host matrix, the spin coherence times in these systems is limited by hyperfine interactions with the host nuclear spins. And finally, we come to donors in direct bandgap 2 to 4 semiconductors. The donors in direct bandgap 2 to 4 semiconductors post similar efficient optical transition as well as we show in ZnO can exhibit long coherence times. This brings us to the question at hand, why zinc oxide? Now, zinc oxide can exhibit long coherence time. It is compatible with microfabrication processes and has the possibility of entanglement generation between zinc oxide donor electron and the donor or lattice nuclei, which is based on hyperfine interaction. This enables electron nucleus register, which was both shown in silicon, phosphorus, and NV centers in diamond, that enables deterministic network scaling in the presence of large photon loss. With that, let's get a historical insight regarding zinc oxides and donors and acceptors in zinc oxide. One of the first papers to be published in this field was by Paul H. Kasai, which was on electron spin resonance studies of donor and acceptor in zinc oxide, dated in 1963. The ESR study was done based on lithium as acceptors and halides as donors and was done on polycrystalline ZnO. The paper was able to establish G factors for lithium acceptors, oxygen vacancy donors, and halogen donors. These G values are interpreted in terms of a picture in which a hole associated with the lithium acceptor is localized in the valence orbital of one of the 4 adjacent oxygen, while the electrons trapped by the donor levels due to oxygen vacancies or substitutional halogen are shared more or less equally among the valence orbitals of the surrounding zinc ions. The next paper, which is a theory of electron and nuclear spin coherence times of shallow donor spin qubits in isotopically and chemically purified ZnO, was done by Jim Tribole in 2009. The paper is a theoretical study of the electron nuclear spin coherence times of shallow donor spin qubits in zinc oxide at low temperature. This study showed that the There was great potential of electron and nuclear spin qubits encoded on shallow donors in isotopically and chemically purified quasi-intrinsic ZnO for the implementation of quantum processor and/or quantum memories. These research papers paved the pathway for further research in the field of donors in zinc oxide, which is our topic at hand. Before dwelling into the theory, I want to discuss the correct state of art, because most of the research that is done today is the basis of the theory of the presentation that I am putting out. So the primary basis of the whole idea is behind the coherence properties of shallow donor qubits in ZnO, which was a paper that was produced by this group led by the chief scientist Kai-Mei Fu. Kai-Mei Fu has a grant from NSF for research in the field of donor electron spins in direct bandgap semiconductors for quantum networks, which lasts until 2021. His team has been working on similar technology and will also provide a future prospect for further exploration. Now on to the setup of the paper and how the levels in zinc oxide due to the donors is used in the whole process as spin qubits. Now the zinc oxide sample that is being used is a 360 micrometer Tokyo Denpa zinc oxide crystal. The sample includes a 0.7 micrometer high purity ZnO epi layer grown by molecular beam epitaxy. The total donor concentration is around 10 to the power 17 centimeter per centimeter cube. However, the measurement signal is dominated by the substrate donor emission. The sample is mounted on a continuous flow cryostat with a superconducting magnet in the voided geometry. You can see in the figure 3.A regarding the magnetic field direction and the optical propagation axis, which is denoted by C. The Zeeman splitting of the D0X state is solely determined by the hole spin, as the two bound electrons form a singlet. The two ground spins up and down in the excited state form the delta system that is denoted by the blue area in the figure 3-bit B. The typical spectra at 0 and 4 Tesla can be seen in figure 3C. At 0 Tesla, the two main peaks correspond to the aluminium donor and gallium donor. At 4 Tesla, the aluminium and gallium peaks each split into 4 peaks due to the electron and hole Zeeman splitting. The polarization depends on the 4 peaks, confirms the gamma-7 valence band symmetry assignment. The D0X states in ZnO exhibit short radiative lifetime approximately of 1 nanosecond and Huyang risk parameter of less than 0.1, which indicate high radiative efficiency in the zero phonon line. The Zeeman splitting for the hole and electron can be seen in figure 3.D, and the G factor of the electrons and holes is also calculated and mentioned. Here the figure 1 shows the Hamiltonian for the 4-level donor system in the interaction picture with the rotation wave approximation. The small omega e is equal to the energy of the electron. In this experiment, the polarization of the laser is so adjusted that capital omega 1, 3, 2, 3, 1, 4 and 2, 4 are equal to omega r. So this gives us the effective Hamiltonian, where omega effective is the effective Rabi frequency. The whole process is designed to provide optical spin coherent control. In order to better understand the dynamics of the density matrix, we use the full 4-level master equation with decoherence and relaxation taken into consideration. A CW pump pulse is resonantly applied on either the down to excited transition or the up to excited transition for initializing the up or down states respectively. Now, in order for the calculation of T1, we observe that even though the high magnetic field dependence of zinc oxide is similar to what it is observed in other semiconductors, the T1 value is 2 orders of magnitude longer than that of lower spin orbit coupling. The longest value is observed at 0.14 plus minus 0.05 seconds at 2.25 Tesla. This is 10 to the power 5 times longer than previously reported spin relaxation times in ZnO layers. At low field, a positive magnetic field of T1 is observed in gallium arsenide and indium phosphide due to the inhomogeneous static hyperfine field and the short electron correlation time at the donor sites. In zinc oxide, this mechanism is expected to be weaker because of small electron bore radius and thus longer correlation time. The high magnetic field dependence together with the small bore radius suggests T1 can approach and possibly exceed seconds at lower magnetic fields. Now we come to the calculation of T2 and T2 star. T2 star is extracted from the decay of Ramsey fringe amplitude as a function of pulse delay time. A fit for the data is shown in the figure using the exponential expression that gives a T2 star experimental value of 17 plus minus 2 nanoseconds. This dephasing time originates from the inhomogeneous nuclear field due to the hyperfine interaction between electrons and lattice nuclear spins. For gallium donors in ZnO, this includes the hyperfine interaction from both the gallium nucleus and the zinc nuclei. Now we come to the theoretical value of the T2 star. Using the effective mass, bore radius, and by combining hyperfine interactions from both gallium and zinc, we find T2 star theoretical to be around 9 nanoseconds, which is in close proximity of our experimental values. Now we apply a spin echo sequence to suppress the effect of inhomogeneous nuclear spin and use a Hahn echo pulse to calculate T2. A standard spin echo includes 2 pi by 2 pulses separated by 1 pi pulse. The measured spin echo decoherence time T2 is equal to 50 plus minus 13 microseconds with an exponential fit. Now, certain possible reasons for limiting T2 include instantaneous diffusion and spectral diffusion. Instantaneous diffusion is the decoherence caused by the refocusing pulse in the spin echo sequence. All of this paints a picture about what are the major factors that make ZnO such a good alternative towards the formation of qubits. It's primarily because of the low values of T1, T2 and T2 star, and at the same time its ability to be highly compatible with microfabrication techniques. This finally brings us to what are the future prospects in the field. The future prospects are, in the near term, as suggested in the paper, single donor isolation for fundamental studies can be achieved with nanostructures fabricated by focused ion beam milling or through the use of single nanowires. In the long term, scalable device integration will require ZnO fabrication techniques to be pushed beyond the standard microfabrication techniques currently developed for ZnO. Now, the biggest factor right now is the purification of the donors and a proper production of high purity zinc oxide. In that aspects, there is a paper on the fabrication of ultra pure anisotropic zinc oxide nanoparticles with simple and cost effective routes, and that's implication by this team that's as provided, and this could pave a way for similar technology being used towards fabrication for quantum bits. Here are some of the references of the papers that I've used in this presentation. With that said, thank you and have a nice day.